On the next homework you're working on, the last problem says take the trim solutions that you got from the previous problem, enter them into a MATLAB script that runs a simulation of the aircraft. So that's what I'm going to show you how to do right now. Is you'll download 2 files from Blackboard. The first file will be MDL, and it will be labeled Simulink model file, something like that. So you need that file, and then you need this one called Learjet student.m, and this is a MATLAB script, and it says this is the one that you will run. So you need both of those files, and then you're going to double click on this file here, learjetstudio.m, and it will open up in an editor, which I have opened up on another screen. So you'll double click on that, and then you'll see this thing here. And it's kind of like Fortran code. It's, well, you guys know MATLAB, right? You guys have taken 227 or you've used MATLAB before. So in this, you will enter your trim values for angle of attack, elevator, and thrust that you did from the previous problem. Make sure that you notice the units that this code asks for. It requires degrees here. So if your solution gives you radians, you have to convert to degrees. So you're going to type in here. 9 is not the correct answer, but it's a number I put in. -2 is not correct, but you type in that. And then 2,000 pounds of thrust. And then the code sets up a bunch of parameters for the simulation. It says, okay, here is the airspeed we're flying at. There's the geometry of the aircraft. Here's the weight. Here's the inertias. Sets up all the aero data parameters. So it's going to feed forces and moments into the full nonlinear equations of motion, including your trim elevator and trim thrust. And then it's going to run that forward in time. It's going to numerically integrate it like I showed you before in the MATLAB script or the MATLAB block that we looked at. And it does that by calling this Learjet model file down here. So that's why you need that file. And when you run this, you'll want to have this window opened up. Double click on it inside MATLAB. And you'll want to double click on learjet.mdl, and it will open up the Simulink model that runs the simulation, as well as some graphs. So when you double click on that, you'll see a new window looking for it. Let me double click on it. All right, there we go. You get a window that looks like this. And here is where the thrust, the elevator, and the alpha goes inside the block here as an initial condition. And then out the other side, it will give you a scope that plots angle of attack, pitch angle, and airspeed in degrees and feet per second. So if you double click on any one of these scopes, you'll get a window that looks like this. And let me share the whole thing so you can see what it looks like on your window here. So you'll get scopes that look like this, and this scope here, and this scope here. those will pop up and you can move them around wherever you want on your desktop. And then you can see the Simulink here. And you'll be tempted when you open this up to push the run button. Don't do that, because you need that M file that sets up all the parameters inside. So you never run this file. You always run the MATLAB file, the .m file that has these values in here that you typed in. So you'll go up and click the green run button, and it will run the simulation. Happens really fast, and then the scopes will show you what the airspeed and the angle of attack do. If this is perfectly trimmed, the lines will be perfectly straight across. It will maintain the airspeed and angle of attack that you found as your solution. So this is a test of how good your solution is that you'll come up with. Don't expect it to be perfect. And in fact, one of the questions is, why is it not perfect? And you'll have to figure that out. Let's say that we made the thrust a lot bigger, 10,000. We're starting out at an airspeed of 170. What would we expect the airspeed to do if we crank up the thrust? Expect it to increase, right? And in fact, that's what happens. You can see we started out here, and there's some oscillation because it's not perfectly trimmed. That's the phugoid mode. You can see the airspeed increases because we cranked up the thrust. So the version that you will download doesn't have numbers here. It has, I think, question marks. And that will also flag you. If you try to run this with a question mark in there, you'll get an error because it doesn't know what a question mark is. Any questions about running that model file or what you're supposed to do with it? Pretty straightforward. Type the 3 numbers in, push the green arrow, and then you'll print out those screens with the scopes. All right, let's see what's next. Oh, we're going to do lateral directional trim. So I'm going to do a majority of this on the blackboard. As soon as I find a marker. So we're going to write down the lateral directional equations. These are the steady state lateral directional equations. So these are the other 3 equations. So this is steady state rectilinear flight. So we're still straight line motion. We're using those steady state equations. Remember, we pulled all 6 of them up, and then we plugged in the forces and moments. So now we have the Y force. So here's the steady state gravity vector. Here's the side force aerodynamic, and then here's the side force thrust. It's pretty easy. Force balance, it's a static equation. It's steady state, statics, no dynamics. Then we have the rolling moment equation in the yaw. And this is a classical moment trim equation. It just says the sum of the moments has to be 0 so that the airplane doesn't rotate. So here's the aerodynamic rolling moment. Here's the thrust rolling moment, if there is any. And you're done. The yaw equation. So there's the aerodynamic yawing moment, the thrust yawing moment. And we have to decide, well, what are the unknowns? We listed these before. Beta, aileron, and rudder, and bank angle, but we already said that to split these up from longitudinal and lateral directional, we were going to specify the bank angle. So we're going to choose that. We're going to say, oh, okay, we'll be banked at 5 degrees, 10 degrees, whatever. And we're going to solve it from there. So these are the lateral directional unknowns. And the longitudinal unknowns, remember, were alpha, elevator, and thrust. And that was the other trim solution. So I have a question for you. The equations that we started with way back in chapter 1 had U1, V1, and W1, P1, Q1, and R1. Where did they go? Well, some of those are lateral, like the velocity, right? And Q and R, those are lateral. Where did they go? Is it a mystery, or do we know? We can make a Netflix series on the mystery here, right? The what? I think you're on the right track. What did we say this is? It's rectilinear flight. So what's the condition for that? P, Q, and R are 0. Okay, so that's where those went. How about U, V, and W? Is there anything up here that's related to U or V or W? Yeah, so beta has V inside it, so that didn't disappear. How about you? Remember, actually up here, one of the unknowns was v sub p, the total velocity. So that's related to forward speed, right? Then how about w? It's related to angle of attack, except we're in stability axis. So remember, in stability axis, w is 0, and alpha becomes an unknown. So that's why we're solving for alpha. So it's not a mystery. I just wanted to go back and you go, well, wait, the equations we had in chapter 1 didn't have alpha, beta, or anything in them. We've just substituted and defined beta and alpha for this special case, or for this case. So the next thing we want to do is solve 3 equations and 3 unknowns. So that's harder than the longitudinal. I lost my beta here. Longitudinal trim problem, and we had 3 equations and 3 unknowns, but we were able to separate out the lift and the pitching moment equation and solve for 2, and then solve for the thrust next, right? So this is a little harder because it's 3 by 3, but we can set it up into a matrix. We'll shove the stuff that doesn't have the unknowns in it on the right-hand side and put a matrix of the unknowns here. So that's what I'm going to write next. So can I erase this? Anybody good? Anybody not good? All right, so here's the matrix. Here's our unknowns. There's the coefficients that multiply those unknowns. Then the right-hand side has the leftover stuff that does not have any unknowns in it. Oh, and I divided the first equation by q bar s, the second equation by q bar sb, and the third one by q bar sb, just because it simplifies things. I want to keep that up on the board, so I'm going to give you a minute to finish copying it down, because we're going to need that in a minute, but I'm going to jump over to my laptop to talk about something else, and then we'll jump back to this thing here and put some numbers in. So I'm going to look around and see if everybody's finished writing. And I'm assuming that the Zoomers are as fast as you guys. Or should we call them Zoomies? Which is actually a store in the mall, right, that sells clothes for skateboarder kids. You guys don't buy your clothes there? I don't either. Okay, can I switch? Are we good? There's the menu. Okay, we're good. Let me fold this over and we'll get going. So the first solution we're going to talk about of this set of equations is, let's say we have a symmetrical aircraft with symmetrical thrust. So what that means is there's no side force from the engines, because the engines are lined up perfect. There's no rolling moment, and there's no yawing moment. We did a good job designing our airplane. The thrust line is perfectly in the XZ plane, no forces or moments. So if we look at the equation that you guys wrote down, here's what it looks like. Oh, and we're going to specify no bank angle. So this is cruise. So that knocks out the sine phi term on the right side, and then everything else is knocked out by the thrust terms. So the right-hand side is 0. Can you tell me what beta, aileron, and rudder are when we solve this problem? This should be a problem on the exam because it's so easy. What is beta? Here's a matrix. Matrix is not singular. So how do you solve this? You take the inverse and multiply it by the right-hand side, right? So what is beta? So here's our vector. Yeah, we get zeros for the answer. So this is super easy. It means if we're flying in cruise at 0 bank angle, beta is 0, aileron is 0, and rudder is 0. And that's really nice. Seems like we did a lot of work to set up this trim problem to stop here, right? So there are cases when the thrust is not symmetric, and that's what we were starting to talk about last time, is when, so this is case 2. It's called the one engine inoperative. Two. And then we'll do a pull up and a turn, but that's a different deal. Of course, they have to name it something fancy. They couldn't say one engine busted, one engine failed. And in fact, on this thing that I think I'll show you later this semester, I think it's in this class, what pilots say about flights is they'll never say that an engine has failed. They'll just say, we have one engine indicating improperly, which really means it's not working. But they don't come on the intercom and say, folks, we have an engine out, we're going to die, because everybody panics. And then what? I'd say it louder. They got to hire me, I'll change all that. Yeah, they hire you, and you'll tell them the truth. Yeah. Okay, so this is the case we're going to do. And so let's draw a picture of it. So here's our airplane. Two engines. Because if you have a single engine airplane and one engine is inoperative, it just means that you're not flying anymore, you're a glider. So if one engine is out, the one on the right is the example we use. There's no thrust, and in fact, you're going to get a little bit of drag from the fact that the engine is shut down, because the propeller is windmilling or the compressor blades are windmilling. And then this engine is still thrusting away. So I think it's pretty clear that we're going to get a yawing moment due to the thrust, NT1. And the book writes this in several different ways. He will combine the two effects together and call it NT1. So really what he has is a total value here. This is the yawing moment due to the thrust happening on the left side, and this is the yawing moment due to the extra drag of the right side. In the book, he has some ways that you can estimate this for an airplane when you're doing preliminary design. He gives this formula. Where this is the TYT, that's T times YT. Let me write that better. YT is the moment arm here, out to the engine. And so you take your thrust times that moment arm and it gives you an estimate. And then he has tables for this FOEI, where you look up if you have a turbofan engine, it gives you a number. If you have a prop jet, it gives you a number. If you have a piston engine, so you just look through those tables and you get a number, and that allows you to at least size things for a preliminary design. For our example, we're just going to be given these numbers here. And let's see, this is in table 4.2, if you ever need it. Yeah, it's from the center line of the airplane, so it's got to be from the CG, like that. So we're going to need these numbers. We're going to come back to this and put numbers in. In fact, I'm going to go back to the board to do this, because we're going to put the numbers into this matrix. In your book is an example airplane with data for a one-engine inoperative condition. This is on page 223 that I'm going to put up on the board. So this is data for a jet engine aircraft, listing the required values. It shows the weight and the density and the forward speed and the wing area that we all need to plug into this equation. And it gives the parameters, CY beta, CY delta A, CY delta R. So these are all the numbers that go into the matrix on the board. So that's what we're going to do, is take these numbers, I'm going to write them up into the matrix, and then we need to take the other numbers here and calculate the right-hand side for that thing. Meaning the MG, sine, phi, cosine, and all of that. And in fact, we're doing this for 0 bank angle right now, but we'll leave it. We'll calculate the other two numbers. So that's what we're going to do next. So let's switch back to the board. You guys wrote down the page. This is in your book again on 223. Is that what I said? Yeah. So I'm going to go in here and write those numbers. And then we're going to calculate these things here. And we're going to say this is small. And right now we're going to do a bank angle of 0, but we're going to change that. So for now, the bank angle is 0. All right, so now we're going to calculate these things here. So this thing on the bottom we're going to call CNT, because it's a coefficient. It's the yawing moment due to thrust divided by Q bar SB. So we're going to plug in the numbers for that. So that's the NT1. And this is the delta ND, so we're expanding this to include that drag component that he includes. So these are numbers. There's our airspeed from the previous table. There's our wing area, and there's B, the wingspan. So the yawing moment coefficient, due to the engine being out, is positive, but then this term has a negative number on it because we moved it over to the other side of the equation. And if we calculate this other number up here for the roll, plug in the number for that, we get minus 0.002. Let me write it big, minus 0.002018. Yeah. CNT is what I'm calling the stuff in here. So it's negative. This is the yawing moment coefficient due to the thrust, and it's negative because it's moved over to the other side. And so, yeah, so here I've actually calculated, sorry, negative CLT, where CLT is the thing without the minus sign. So we've got numbers. If we plug into MATLAB and solve this 3x3 problem, again, we're at 0 bank angle. The solutions that we get are, I'll write it over here. So this is from MATLAB. You guys all know how to solve a matrix in MATLAB or Maple, right? So you plug the matrix in, you plug the right-hand side in, and you tell it to solve it. So we look at this and we go, okay, we need a whole bunch of rudder, a bit of aileron, and we end up with some beta. So physically, what's going on? And that's the solution. So let's go first. Let's see. We want to notice. We'll come back to this in a minute. Sorry. We're going to go back to the picture of the airplane with the thrust. So it looks like we need rudder. Why do we need the rudder? Yeah, fundamentally, it's got this big number that's the yawing moment, right? So I'm going to write that up here. So here's our picture of our airplane. We've got this big yawing moment from the thrust going like that. And so we need a negative yawing moment to counteract the positive yawing moment due to the thrust. So that's why we need the rudder. I'll draw a big old rudder here. We need a rudder deflected like that. It almost 25 is pretty close to the mechanical limit probably for the rudder. And so that's going to produce a yawing moment to counteract that. But the rudder deflected that much is going to give us a side force in that direction. Which is going to push the airplane to the right, and that's what causes the beta. So the way you can think about this is you need rudder to counter the thrust yaw moment, and then the side force due to rudder gives you some beta. And then we got beta, and then the rudder's deflected, and we know that the rudder, because the tail sticks above the CG, produces a rolling moment, and we know that beta produces a rolling moment. The rudder's going to roll us to the right, beta's going to roll us to the left, so that's why you need some small aileron, not a big amount, to balance out the rolling moment. Otherwise, the airplane will start to roll. So the numbers are up on the blackboard, but the physics is you need a rudder to counteract the yaw due to the engine because the rudder sticks above and it creates a side force. An unintended effect, we get some side slip, and you need some aileron to counteract the roll due to both of those. The other thing to notice is that as the velocity goes down, this term that's on the right-hand side goes up because the velocity is in dynamic pressure. So you have less dynamic pressure. And if that term gets bigger, then you need more rudder. Because you have less rudder power because you have less air flowing, less dynamic pressure flowing around the rudder, and so you get less yawing moment. The engine's still cranking away, but the rudder is less effective the slower you go. So in fact, this sets up a situation where at low speeds, you need to be able to calculate how much rudder you have and whether you have enough rudder to counteract the yawing moment. And that's why the King Air that crashed out at Mid-Continent or Eisenhower, it took off, so it was going at low speed. The engines were at max thrust to climb, and that's when an engine failed, and so he got the maximum yawing moment out of the engine, and he was going slow, so the rudder was at its limit as far as being able to control the airplane, and he got too low and too slow and stalled out and crashed. Now the 3x3 problem requires a lot of calculations to make happen, but there's an approximation we can use, and I'm going to switch back to the board so we can talk about this. Since the major effect that we've got going on is that we need rudder to counteract the yawing moment, and we saw that we didn't get a whole lot of aileron and a whole lot of beta, although we do get some, the biggest player in this is this bottom equation, because that's the yawing moment equation. So that's the one we can use to solve for rudder. And if we notice that this number here is small, that's the aileron effect, the yaw from the ailerons. We get some, but we can make an approximation and say, okay, this is the biggest number here. That's smallest, so maybe we can shortcut this 3x3 problem and just calculate the rudder that we need based on that equation only. So as an approximation for doing preliminary design, we're just going to use the yaw equation. It looks like this. And if we say that beta is small, we don't want to fly at a huge beta, so we're going to say if beta is small, then we can use this equation really quickly to solve for the rudder that we need to counteract the yaw. So another approximation, we're going to say beta is small. And we divide by Cn delta R, where we're solving for rudder. And I'm going to write out the dynamic pressure. So for any airspeed, we can find out how much rudder we need to counteract this full throttle engine yawing moment. So for our example, we can plug in the numbers. I'm going to need more room than that little box. So we're just using the numbers from this equation here, the 001, and then the thing we had on the right-hand side. Remember we calculated CNT. That's this thing divided by 1/2 rho V squared SB, so that's all that we calculated prior. And we get 14.3 degrees. What did we get earlier? 3 by 3, we got 25 degrees. That's an estimate, but it's not real great. So what's the problem? Why didn't we get a better number? It's because we did have some beta. Here we said beta is small, but we actually had, what was it, 3 or 4 degrees of beta, which is significant beta. So that's why this is different. And in fact, if you plug in the value of beta into the full equation, you don't neglect the beta, then you find out you get pretty close to the right rudder amount. But we don't know what beta is because we haven't solved the 3 by 3. So you say, well, why is this useful? If you look at the regulations for one engine out conditions, they allow you to bank the airplane up to 5 degrees. And by doing that, if you bank the airplane, you can get some beta. You get an effective beta that then causes the rudder to be bigger. And so it turns out that if you allow a bank angle of 5 degrees, then this actually predicts the amount of rudder that you need. So it sounds kind of kludgy, doesn't it? But from experience, they found out that you can use that approximate formula if you allow a bank angle. And where does the bank angle show up? It shows up in that right-hand side, right, for the side force. So if you put 5 degrees of rudder and bank angle in there, so let me write that on the board. So we're going to go back to the full 3 by 3. And put in a bank angle of -5 degrees. You can do plus or minus, but it turns out for this condition, a -5 degrees helps you out. Then our matrix problem has a number here. That we calculated with 5 degrees in that formula. Do you remember what? Let's go ahead and calculate it. So this is that term that's minus mg sine phi cosine gamma over q bar s. If you plug in 5 degrees, convert it to radians, take the sine, we're still flying level. Plug in mg q bar s, you get that number that I've listed up there. And so if you plug that in up here with the other numbers that we calculated before, and solve that same 3 by 3 matrix problem, then here's the solution you get. So we get a beta minus 1, ailerons of minus 2.2051, and a rudder of 11.35 degrees. So if you allow that bank angle, that side force, the side force due to being banked actually helps you counteract part of the yawing moment because it generates some side slip that then helps you balance the yawing moment. And this is pretty close to that 14 degrees that we predicted with the approximation. So again, logic here, what happened was they calculated this for 0 bank angle, realized they could allow the pilot to bank 5 degrees. If they do that, then that approximation actually matches the 3 by 3 solution pretty well. And again, this is preliminary design. They will do tests on this. They'll do wind tunnel tests and flight tests to validate the approximation and the numbers. You'll see this quite a bit in preliminary design because you want to, when you're designing the airplane, you don't want to spend a month doing these calculations to design and size your rudder because you want to get other things sized as well. So it's nice to have these approximations so that you can get your airplane sized approximately and then you can refine it after that. Because if you're doing trade-off studies along the way, you need to be able to do quick calculations. So all this leads to calculating how slow can you go and still operate the airplane with an engine out. Remember we talked about if the velocity goes down, you get less rudder power, which means you need more and more rudder to keep from crashing. So what you want to calculate is something called the minimum controllable speed. And it comes from that same formula that we used to calculate the approximate rudder. So this is the yaw only approximation, which we found out is good for about minus 5 degrees bank. So if we allow the airplane to bank a little bit, it helps out. And then the rudder can be calculated from this approximation. Again, for any airspeed, right? But I said, how slow can you go and still control the airplane? That's going to be determined by the maximum rudder deflection that you can get from the airplane. Rudder pedal full in, the rudder's over against its hinge limits, its mechanical limits. And then that is what we call the minimum control speed. It's squared in the formula. And so you can calculate it directly from this formula. You simply solve for VMC. It's going to be the square root of the delta R max times all the other stuff. And this is where the experience of the FAA and the military come in. Part 23 and 25 say that your VMC, your minimum control speed, must be less than 1.2 times stall. Then the military guys say your minimum control speed must be less than 1.1 times stall, or V stall plus 10 knots equivalent airspeed. So all this is saying is that you've got to be able to fly close to stall with an engine out and not crash. And so you need to prove that you have enough rudder power. Where's the rudder power? It's right here. Enough rudder power to fly near stall with one engine out, because it can happen. So there's three things that are, I guess, priority, and what we've talked about today with this is we're solving the lateral directional trim problem, so we put it into a 3x3 problem. That's what you do to get the most accurate values. And in the next homework, not the one you're working on now, you'll do the 3x3 problem and find out VMC from it, and then compare it to what you get from the calculation. So you can see how well it does. So we have the 3x3 trim solution for one engine out, and then we have the approximation, so that's the second thing. But fundamentally, I want you to be able to explain to your husband or wife or spouse or boyfriend or girlfriend or kids or grandparents, I want you to be able to draw a picture and explain why one engine inoperative is a problem and why it's important and why the rudder is there. So that's where we talk through that you need the rudder to counteract the yaw from the engine. Then you get some side slip because the airplane pushes sideways, and then you need some aileron to counteract everything. I think that's important to be able to do just in life with everything. Right, when you go to your doctor and he starts spouting Latin words as to what's wrong with you, you want the bottom line and, how does that affect me and what do I need to do about it in non-medical terms. So you guys are kind of becoming doctors of airplanes, right? You need to be able to explain stuff that happens. If an airplane crashes and somebody that you know that doesn't know aerospace asks you about it, you can sound important and talk about it and feel good and impress your friends and neighbors, right? Yeah. Oh, this is mil specs. It says stall speed plus 10 knots equivalent airspeed. It's just the way that the instrumentation on the airplane measures their true airspeed. It's, remember, well, I guess it was on the board, right? Equivalent airspeed versus true airspeed has to do with whether you use sea level density or the actual density when you're estimating airspeed. There's all kinds. There's KIAS, which is knots indicated airspeed. There's knots true airspeed. I don't know them all. How are we doing on time? Because I'm done. You guys ready to go home? That's close enough. The numerator? Oh, both of those cause the same yaw, right? If this isn't the drag, this is subscript. This is the yawing moment due to that drag. So the thrust causes a yaw like this, and the backwards drag causes a yaw in the same direction. All right, let's call it good for today.